So energies in simple harmonic motions are basically of mainly of two type. Okay, the kinetic energy and the potential energy, not the gravitational potential, but only the potential energy, right? So these are the two type of energies that we will going to have in our oscillation. Okay, and when we sum up, so we'll get the total energy, right? So let's start with the energies. Hmm, come on. 31 and this one, and we have energies in SHM. Okay, so to understand the concept of energies, let's assume that, or let's assume a pendulum. Okay, let's say this is a pendulum we have. Okay, by the way, we are doing the things with the purple and the green. Yes, yes. Okay. So let's say this is the pendulum we have. If we try to understand what will be the displacement and the energies of the pendulum, so let's see what should we get. Come on. Okay. So we know that the velocity, the displacement will be zero at this position. Okay. The displacement will be zero at this position. Okay. And the velocity will be maximum at this position, right? From the previous knowledge, we know that. Okay. And we also know that the acceleration is also zero in this position, right? And as we move from mean position to any one of the extreme position, right? So the displacement will going to be the maximum, okay? And the velocity will going to be the minimum or zero, okay? Because you know that at maximum height, the velocity will be zero, right? And acceleration will be maximum again, right? Maximum, but in the opposite direction, okay? So velocity and acceleration both should be opposite to each other, right? Now, using these ideas, if I ask you what will be the value of the kinetic energy, or what would be the state of the kinetic energy, will it be maximum or like minimum at this point, starting point? What do you guys say? Any idea?
Maximum.
Maximum, perfect. And GPE, not GPE, just PE, okay, potential energy. Potential energy is basically the energy stored in a body due to the positional change, okay? So the potential energy is going to be minimum, right? And there will
Can
be,
we
sorry,
can we say zero?
yeah, we can say that. We can say that. Okay, and total energy at this point is going to be only in the form of kinetic energy, right? Okay, so this is the first thing. Now, the second thing is if we talk about this one, so for this one, the kinetic energy is going to be zero, right? Zero. And potential energy is going to be maximum. and total energy is going to be in the form of potential energy, right? Okay. So total energy is in the form of the potential energy, right? So these are the two extreme positions, right? Now, if we talk about the position that is in between the two extreme position, so let's see if we are talking about, let's say, this position. Okay. Okay. So at this position, come on. Okay, let me just draw the black line. Okay. So at this position, the kinetic energy, the displacement will be smaller than zero maximum, but greater than zero, right? Similarly, the velocity should be greater than zero, but smaller than maximum. Or you can say that greater than, yes. And acceleration would also be in between maximum and zero. Right?
Uh, s-
Yes.
the velocity shouldn't be greater than maximum. Oh
No,
no,
not
no.
greater than
Oh,
maximum.
okay, my bad, my bad. Sorry.
Okay. Now, if we talk about the kinetic energy, so it will also be like for everything, there'll be the same concept. Okay. Wait. Okay. So kinetic energy will also be in between. Potential energy will also be in between, and total energy will be the sum of kinetic plus potential energy, right? So this is the concept of, or this is the conclusion of the quantities that we have in this scenario, right? Now, from this concept, we have to figure out what will be the values for like what will be the formula for the kinetic energy and the gravitational potential energy, or the potential energy only, and the total energy. Okay. So, okay, let's see. So starting with kinetic energy, okay, we can use the formula directly. Okay. So if we use, okay, so for kinetic energy, for kinetic energy, okay, so you can use this formula. Ke is equals to half mv squared, right? This is the first formula. But the problem is that the oscillation is basically dependent upon the position mainly, right? We relate the oscillation mainly with the position. Okay. So if you have to relate the kinetic energy with the position, then you have to use a formula for the velocity that relate the velocity with the position, right? And that was what we studied as omega and under root x naught squared minus x squared. Okay. So if you guys recall this formula, okay, I think I missed omega in this displacement. Yes. Okay, sorry, I missed the omega in this concept. Okay. Wait. Let me just add omega right here. Omega. Okay. So this is the formula, right? Now, so omega is right here. If you want, if you want, you can add plus or minus sign with it. Okay, but if you don't, then you can ignore it, right? So this is the formula for the speed. Now the kinetic energy is going to be half m, and then put the values in omega, and then under root x naught squared minus x squared, okay, and whole square, right? Then kinetic energy is going to be half m, and then omega squared, and then x naught squared minus x squared, okay. We generally use this formula, or we generally will generally be using this formula for the kinetic energy, right? So kinetic energy at any instant is given by this formula, okay, clear? Now this is the first concept, right? Now if we say, if we pick the point A, let's say this is the point A, um so this is the point A, this is the B, and let's say this is the C, okay. So if we pick the point A, and if I say that for point A, for point A, okay, we know that the displacement x is 0, okay, and we also know that the total energy is given by the kinetic energy only, right? If we substitute the things in the kinetic energy formula, then so total energy is equals to the formula of kinetic energy, which is half m omega squared, and then x naught squared minus x squared, okay. And in place of x, we can just replace it with 0, right? Because we know that the displacement is 0 at that position, okay. So the total energy will going to be half m omega squared, and then x naught squared, okay. So this is the formula that is going to be useful for the kinetic, for the total energy, okay. Now, as a by the way, some student uh, confuses this formula with the kinetic energy formula. They say, okay, we derive this thing with a formula, with a kinetic energy formula, so it will actually only work for point A and not anywhere else, right? But if you imagine, or if you just look closely this formula, so this formula contain nothing that changes as as the oscillation move on, okay, or as a pendulum move from one position to another position, right? Everything is constant, right? Because if you have a system and that system is oscillating, right? So it will have a fixed amplitude, right? It will have a fixed frequency, right? It will have a fixed time period, right? It will have a fixed mass, right? So the total energy contain all of the variables that are fixed, okay, that the amplitude is fixed for a specific oscillation, the omega, the angular frequency, is going to be fixed for every specific oscillation, the mass is going to be fixed for a specific pendulum, right, or a specific system, right? So that is why there isn't any quantity in this formula that is changing. So we can say that this formula work for like any point of the oscillation, right? So because we are actually not working for any point, we're just working for the specific point, and the total energy at a specific point should remain the same at any point, right? Because we say that the total energy remains the same, so it will work for every point in the system, right? So total energy, like this is this formula gives the total energy of the oscillation. Okay. Now, the last thing is the potential energy. Okay. So to understand the potential energy, we must have to consider the point B. Okay. So we know that at point B, um, okay. So let's say at point B, okay, we know that the total energy is basically the summation of kinetic energy plus the potential energy. This is the first case, right? Then we have Okay, so we know that the total energy is given by half m omega squared and then x naught squared. And we also know that the kinetic energy is given by half m omega squared x naught squared minus x squared, okay, plus the potential energy, right? If you expand the kinetic energy, so you will get half m omega squared and x naught squared is equals to half m omega squared x naught square minus half m omega square and then x square plus potential energy, right? Now we can cancel these two things out, okay? We can cancel these two things out, okay? And we'll be left with the potential energy, potential energy equal to half m omega square and then x squared, right? So this is the formula for the potential energy, right? Okay. By the way, you don't require to remember the derivations. Okay, they're just for the sake of understanding. Okay, if you want to ignore them, you can ignore them. Right? They will only ask you to apply the formula and not to drive it. Okay, so yep, that's only for your easiness. Okay, now that's done. Okay, okay, fine. So these are the three formula for the energies that we have. Okay, the kinetic energy, the potential energy, and the total energy. Right? Be like you have to remember the formulas and that's it. Okay. So now let's move on. Let's move on to their graphs. Okay. Okay. So I don't have any other thing. Okay. Can you guys tell me? By the way, can you guys tell me what will be the displacement exactly in the center of the oscillation? When the velocity, or what will be the relation between the position? Okay, sorry. So what will be the displacement of the velocity in the center of the oscillation or at the point? Okay, let me just write the question, otherwise I'll confuse myself. Okay. uh the displacement of the oscillation, okay, when kinetic energy is equals to the potential energy. Okay, so this is the point we are working at. Okay, for like when kinetic energy is equals to the potential energy, what will be the displacement of the particle in terms of amplitude? You can say that, like if the amplitude is one centimeter, so will the displacement be half when kinetic energy equals to potential energy, or will it be different? Okay, so this is the question. Okay, to answer this question we have to consider the formula. Okay, so since we are saying kinetic energy is equals to the potential energy, so we have the formula for the kinetic energy: half m omega square and then x naught square minus x squared, okay, is equals to half m omega squared and then x squared. This is for the potential energy. Okay, so these are the formulas. Okay, now these things are cancelled out. Okay, or you can cancel this out, and this out. Okay, so you can cancel these things out. Okay, and on the left hand side they also get cancelled. Okay, so this get cancelled, right? So you're left with x naught squared minus x squared is equals to x squared, right? So if you solve it, you will get x naught squared is equals to 2x squared, okay? and then it will be x naught over 2 and whole thing under root. Okay, gives you the x. Okay, so x is going to be x naught divided by root 2. Okay, and root 2 is basically 1 over root 2 is basically 0.707. Okay, so this will going to be, okay, this will going to be x is equals to 0.707 of x naught, right? Which mean when kinetic energy is equals to the potential energy, the displacement will be 70% of the amplitude. Okay, is that clear? Perfect. Now these are the concept for the energies in simple harmonic motion. Now we have to discuss their graphs. Okay, so to discuss the graph, we have to understand the relation. Wait. Okay, now I have this and this and um graphs in SHM. Okay. So we have to understand some type of graph, okay, and then we'll be done with that concept, and there'll be one concept remaining after the graph one. Okay. So okay, for to understand the graph, we have to copy the previous thing out. Mm, we have to consider this case, these cases, okay. So let me just have it. Okay. Uh, I just want these, copy and paste. Okay. Okay. So you know that kinetic energy, sorry, potential energy is basically related with the displacement. Kinetic energy is related with the amplitude. Oh, sorry, kinetic energy is related with the velocity, right? So that's why I copied this graph, because I will going to use them, or I will going to be making them as a reference, okay, and use them to draw the energy graph, okay. So let's first consider the displacement graph, and I'm using that graph to draw the velocity, sorry, to draw the energy graph. Okay. Okay. So now this is going to be the energy graph. Okay. So this is displacement and then potential energy. Okay. So this is the graph for the potential energy, right? So potential energy will be minimum at the minimum position. Okay. Potential energy will be minimum at the minimum position. So there will be first point. Potential energy will be maximum when the displacement will be maximum. And then potential energy will be minimum at the minimum position again. Right. And then potential energy will be maximum at the maximum position, but it won't get negative, because you know that potential energy is basically the scalar quantity. So it does not get negative. Okay. And then it will be zero as it gets zero. Right. So, oops. Okay. Now, if we draw the graph, if we try to draw the graph, so the graph looks like this. Okay, come on. Wait. It basically not look like this, like this, and then like this, and then like this. Okay. Or like this, and like this, and like this. Okay. So this is going to be, okay. So this is going to be the potential energy graph. Okay. Mm, like this. Perfect, perfect, and perfect. Right. So this is going to be the potential energy graph. It won't get negative because you know that the potential energy is maximum when the displacement will be maximum, and it will be zero when the displacement will be zero, right? Now, if we draw the kinetic energy graph, if we to draw the kinetic energy graph, we have to consider the velocity time graph first. Okay, so let's bring the velocity time graph from the above one where we make it. Okay, so gone, and okay. Now let's just copy the graph, this one, done. Copy and paste right here. Okay, so fine. So now this is the graph for the kinetic energy. Okay, for the velocity, and then we will be going to we will going to use them for energy. Okay, we will going to use them for for energy. If you want to change the color, you can change it to, let's say, some maroon. Come on, maroon. Okay, so this is a velocity graph, right? And corresponding to the velocity graph, if we try to draw the kinetic energy graph, so it will look the same as this one, but a bit different because it should start from the maximum value. Okay, it should start from the maximum value. Okay, so and I have, let's say, this horizontal line. Okay, and we will going to be using, okay, let me just enlarge this one, and then this one, and then this one, and then this one. Okay, and yep, perfect. Okay, fine. Now, if we draw the velocity one, that is extremely bright. If we draw the kinetic energy graph, so kinetic energy graph would look like this. Okay, so kinetic energy will be maximum at the maximum velocity position. Okay, it will be maximum. And maximum, and then kinetic energy will be zero. Then kinetic energy will be maximum again. It won't get to in the negative position because it is energy, and it is a scalar quantity, right? So this is going to be the graph for the kinetic energy. Now let's draw it. So this is something I have. Okay. So this is basically the energy graph for the potential energy, right? So this is the potential energy graph if it want perfect. So a potential energy graph, right? So one oscillation of the velocity gives double the kinetic energy oscillation, right? And yep. So So yeah, this is the main concept for the graph of the simple harmonic motion. Okay, they can ask you by giving the graph of the displacement or the velocity. They can sometime give you the graph for the displacement. Okay, let's say they give you this graph. Okay, and instead of asking the potential energy, they ask you to draw the velocity time graph using the first graph, right? So if the velocity time graph is given, then imagine this graph first and then go to that one, okay? Because you know that where the displacement will be zero, the velocity will be maximum, right? So you have to use that concept and you have to move to the kinetic energy one, okay? And they similarly, they can give you the velocity time graph, okay, and then ask you to draw the potential energy graph, right? So you have to look at this graph and then you have to imagine this one and then you have to back to that one, okay? So this is how you can make the graph, right? So that's it. So in the next class we will probably discussing the remaining concept, one remaining concept of the simple harmonic motion. Then probably we will be ending this chapter tomorrow, and on Sunday we'll be doing the question, okay? So on Saturday, basically on Saturday we'll do the question, okay? So now, okay, that's it for today class, guys. Take care. Love is.
Love is.
Love is.